Log on, tune in, find out. Another good idea from Cambridge.
Falconer from the University of St Andrews, who will speak on affine sets and measures.
Self-affine.
Self-affine sets and measures.
Okay, well, thank you very much for the hospitality on this programme. Possibly my main interests are in geometric measure theory, which many parts of these days get termed fractal geometry because it's a trendier term. So why am I at a discrete analysis programme? Well, I think there are a number of answers. For the first one, there are many problems in discrete geometry which have analogues in measure theoretic analogues. One of very contemporary interest, we've heard of that the Erdos distance problem has been solved, or at least solved within a square root of log n by Guth and Katz very recently, and there is a measure theoretic analogue of this problem, namely how small does a subset of the plane have to be in the Hausdorff dimension sense to guarantee that the distance set, namely the set of distances realised between pairs of points in the set, has positive Lebesgue measure. And these problems are related, but they're also very different. And then, secondly, many problems that I work on very much depend on an underlying discrete structure. And this will be the case with much of what I'm going to be talking about today. Namely, you have some sort of graph or tree, ultrametric space, on which you set up various structures, and then you have to transfer this to a continuous space, Euclidean space or something like that, either an embedding or an immersion or something like that. And in fact, many of the problems arise in this transference process from the discrete to the continuous. So that's relations with discrete analysis. So today I'm going to talk about a subject that's interested me for quite some time, namely the structure of properties of self-affine sets and self-affine measures. And since I imagine many of you will be fairly unfamiliar with this, I'm going to give a introduction and survey of the area, and then I'm going to end with some recent work on the subject. So let's go back to basics. I hope that these, hope you can see this okay on the visualizer. Is that readable at the back? Not completely focused. How does one focus these things? It's supposed to focus automatically, I think. If you prefer, I can work with the side overhead projectors, which are sort of more conventional. Would that be any better?
Yeah, I think probably.
Oh, you think? Okay. So I will stick with these rather than the visualizer. I did have reservations about using it. So I hope you can see this reasonably well. So let me start by introducing iterated function systems to those of you who are unfamiliar with them. An iterated function system is simply a family, usually, well, for our purposes, finite family of contractions. So just using vertical bars to denote distances between 2 points. The images under each of the mappings Ti of any pair of points is no more than some constant, strictly less than 1 times the distance between the original points. And there's an underlying result that if you've got such a system of contractions, then that guarantees there exists a unique non-empty compact subset of the space. And I'll just work in Euclidean space, but all of this can be extended to more general metric spaces. There exists what's called an attractor or an invariant set with the property that it's the image of its, equal to the union of its images under these contractions, and within the family of non-empty compact sets, that attractor is unique. And then if the transformations are similarity transformations, we refer to this set E as self-similar, Otherwise, if there are affine transformations, we refer to the attractor as self-affine, and then there are various other possibilities if you have nonlinear transformations, and indeed these ideas through Markov partitions relate to questions on dynamical systems. And there's a very elegant proof of this result, in fact, using Banach's contraction mapping theorem. You simply look at the map of the space of non-empty compact sets to itself given by mapping a set to the union of its images under the TI. You can show that as a set transformation, that is a contraction with respect to the Hausdorff metric, and the Hausdorff metric is complete provided you're working in the environment of a compact space. So let's just say a little bit more about this. Once you've got this set up, let me come over here. I'll be drawing pictures like this. Once you've got this set up, in fact, there is you can construct this attractor E by taking any sufficiently large set, ball, whatever, and looking at its images under the transformations and their iterates. So the images of your large set under T1, T2, T3, just for example, are these larger regions, and then the second order iterates Ti, Tj of your original set are sub-regions and so on. I'm assuming we're not getting any overlaps and so on, in which case the picture gets much more complicated. And so the words consisting of integers from 1 to m, if there are m transformations, give an indexing of these various islands, and one can extend this to index the points of the set E by looking at the points in any nest of islands. So we define xi to be the limit of the image. You can take any point and look at the limit of its images under a composition of transformations as k goes to infinity, and then the attractor, the invariant set, is simply the union of these points over all infinite words. That's not necessarily an injective mapping. You can have overlaps, and then some points can be related by many words. So very trivial example of this is the one people meet first, the middle third Cantor set. You simply write down two contractions, one just scaling by a third, one scaling by a third and shifting along a bit, and then the middle third Cantor set there is obviously the unique set that satisfies that condition. And then by working with more complicated geometrical objects in the plane, here are some instances of self-similar sets, the familiar von Koch curve, a variation on the snowflake, and then a spiral example. And you can see how these, this one, for example, is simply defined by two similarity transformations, one that maps the whole thing onto that bit and one that maps the whole thing onto that bit. And so those are the sort of things one might think about for self-similar sets. And then here's an instance of a self-affine set. Here the three transformations are defined by mapping the square onto each of the three rectangles in the obvious linear way, and then the attractor is this sort of slightly fern-like thing. So those are the sort of objects that I'll be talking about in a much more general setting. And I'm going to be interested in the size of these objects in a sense, and to do this we need the notion of Hausdorff measure and dimension, which I'm sure most of you are familiar with, but just a quick crash course. For a subset of Euclidean space or metric space or whatever, for each positive number delta, let's get this focus slightly better. For each positive number delta, one looks at coverings of my set E, in any set E at all, by small sets UI, small in the sense that I'm restricting my coverings by countable collections of sets, all of whose diameters are at most delta. I'm adding up the s powers of the diameters of all those sets, and I'm taking the smallest answer I can possibly get over all coverings, and that's the definition of Hausdorff cream measure. And then I simply notice that as delta gets smaller, I'm reducing the allowable coverings when taking this infimum, so the infimum will increase or at least not decrease as delta goes to 0, and so the limit exists, perhaps 0 or infinity, and we call that the s-dimensional Hausdorff measure. And then the Hausdorff dimension of my set is simply the value of Hausdorff measure where you get a jump from infinity to 0. So you can show that for small values of s in a given set E, the s-dimensional Hausdorff measure will be infinite. For large values it will be 0, and there is a particular number where it jumps from infinity to 0. It may be positive and finite. If you're lucky, it may be infinite or may be 0 at that jump point. So that's just a reminder of Hausdorff dimension. Another way of thinking of it, if you just forget the delta, the Hausdorff dimension is the smallest number such that this infimum with no restriction on the sets is 0. So, okay, well, one asked how one goes about calculating dimensions of these various objects, and the case of self-similar sets is fairly straightforward. For a self-similar set, there is a natural scaling formula which invariably gives the answer. So we simply, if the TIF similarity transformations, by which I mean an isometry and a direct scaling about the origin by a factor Ri, then very often the Hausdorff dimension is given by the solution of this equation, that number s such that the sum of the scaling ratios equals 1, provided there is some sort of separation going on. So provided in this picture the regions don't overlap too much, otherwise you can get a reduction in dimension. So, for example, you can get that the von Koch curve has dimension log 4 over log 3, and the heuristic argument is simply to note that because Hausdorff measure scale, s-dimensional Hausdorff measure scales by lambda to the f, if you scale your object by a factor lambda, it follows, using the fact that the von Koch curve is made up of 4 copies of itself, each of which are at scale 1/3, that you get the dimension log 4 over log 3. There's a heuristic way of showing that just by using the fact that the measure of the whole thing is the sum of the measures of the individual parts, and looking for the value s where you can assume that the jump value s, the Hausdorff dimension, you get a positive finite answer for measure, but it needs a little bit more work to show that rigorously. Okay, so that's self-similar sets. What about self-affine sets, which is really what I want to talk about today. And life here becomes much, much more complicated. And let me try and illustrate with the following example why this is the case. So let's just have a system with 2 transformations, T1 and T2, that are defined by mapping the square onto the large blue square onto these red rectangles of side 1/2 and 1/3, with the obvious retention of orientation. And so if one looks at the attractor one gets in this case, then you can see by repeatedly nesting these rectangles that get the ratio of the length to the height gets longer at each iteration, that you home down on sort of something that's sort of almost made up of line segments. And in particular, the projection onto this axis has positive length. Provided you have a displacement lambda there, in fact, you can show that the projection of the set E onto that axis has length 2 lambda without too much difficulty. And since you can show that orthogonal projection does not increase dimension, and the dimension of this segment is 1, that means the dimension of the set E has to be at least 1, provided lambda is greater than 0. However, if we now take lambda actually equal to 0, then the whole thing collapses onto the vertical axis. And in fact, it's very easy to see that the attractor is simply a copy of the middle third Cantor set sitting in the vertical axis. And the dimension of the middle third Cantor set is easily seen to be log 2 over log 3, which is certainly less than 1. So the point I'm trying to make is for self-affine sets, although the components are still very well spaced here, the dimension is not continuous in the underlying transformation. And in more complicated examples, this sort of lining up can occur in very, very, very subtle ways, which makes calculation in general of dimensions and so on of self-affine sets really rather difficult. So let's think about what we can actually say. So let me put this over here. So coming back to my same picture, this is just a copy of what we had before.
So in that previous example, when lambda is bigger than 0, you get kind of a copy of the Cantor set. It's just that because it kind of spread out.
Yeah. The projection onto the vertical axis is still the middle third Cantor set, but the stretching in the other direction dominates, and then at that point it ceases to.
But it's not that you're stretching the points; it's that the points are just spreading.
Okay. You're stretching the rectangles of the construction in a sense. I mean, when lambda equals 0, then you could just do all your entire construction within the vertical axis. Yeah. So, what about dimensions of self-affine sets? This is the picture we had before, and this notation for the various regions. I'm going to assume I'm starting my construction with a disk or a ball now, and I will, and therefore, because these are affine transformations, these islands will all be ellipses, and I'm assuming that, therefore, because I'm working with affine transformations, they consist of a linear part, which I'm going to denote by Li, fixing the origin, and then a translated part, Ai. And so let's think about how one might go about finding the Hausdorff measure or Hausdorff dimension of an object one gets in this way. So we need to consider sums of the form, the sum of the diameters of small sets to the power s. And so let's suppose that one possibility would be simply to take the ellipses of this construction, and I'll refer to ellipses because for the purposes of exposition I'll assume I'm working in the plane, but obviously ellipsoids in high dimensions. I could take these ellipses themselves as a covering to try to estimate, to get an upper bound for the Hausdorff measure. So that's one possibility. But if there's a lot, depending on the way the transformations interact, some of these islands could be very, very long and thin, and on a very, very small scale after a large number of compositions. And so you might have one of these ellipses long and thin, and let's suppose that it has semi-axes of lengths alpha 1 and alpha 2, major and minor semi-axes of alpha 1 and alpha 2. If I just use this single set UI, this single ellipse UI as a covering set in trying to estimate Hausdorff measure, then the contribution I will get from that set is simply, well, the diameter of UI to the power s, in other words, alpha 1 to the power s, or rather 2 alpha 1 to the power s. I'm not worried about constants. But the other thing I can do is to take this long, thin ellipse, and I can chop it up into roughly square bits, roughly round bits, the same horizontal and vertical sizes, dimensions roughly, if you like. And if I do that, then, well, how many have I got? Alpha 1 divided by alpha 2, roughly. And these are more or less squarish, and the diameters are going to be something like the order of magnitude is going to be 2 alpha 2, or just alpha 2. So if instead of taking my UI as a covering set, I take all these bits as covering sets and add up their diameters, then instead of having alpha 1 to the power s there, I can get, I've got alpha 1 over alpha 2 of them, times alpha 2 to the power s, which is alpha 1, alpha 2 to the s minus 1. And if f is 1, that actually gives me a smaller answer than just alpha 1 to the s. So by, if necessary, taking these components of the iterated construction and chopping them up in this way, we can actually get much smaller sums of powers of diameters for estimating Hausdorff dimension. And this actually turns out to be the key of how one tries to work with self-affine sets. So let's be a little bit more precise about this. For a linear transformation L, it's convenient to define the singular values of the transformation, and again I'll just do this in 2 dimensions, to be the length of the semi-axes of the image of the unit ball under L, if you prefer square roots of the eigenvalues of positive square roots of the eigenvalues of the product of L with its adjoint. And then, following what we saw over there, I'm going to define something I call a singular value function by phi s of the linear mapping to be equal to alpha 1 to the s, that's just the larger singular value to the power s, if s lies between 0 and 1, and this other product, alpha 1 times alpha 2 to the s minus 1 for s lying between 1 and 2. And more generally, in higher dimensions, you have, in n dimensions, you have n singular values, and the analogue is the product of the first. If s lies between m minus 1 and n, then you take the singular value function to be the product of the first n minus 1 singular values, and the last to some power given by this difference, s minus n plus 1, that will lie between 0 and 1. And there are 2 very useful properties of the singular value functions. Firstly, they're submultiplicative. The singular value function evaluated on a product of 2 linear transformations is less than or equal to the product of the singular values. And secondly, provided we're working with contractions, then this expression for any linear transformation is decreasing, strictly decreasing in S. It turns out to be very rather useful properties in what we do. So let's come over here again, this picture. So with our affine transformations, because of the way we've constructed this, and I've started with a large ball or disk such that the image, the M images lie inside it and don't overlap. Non-overlapping is basically for the convenience of drawing the picture. So the attractor will lie in any case level, the union of any case level collection of islands in this construction case, and they will be ellipses because I'm taking B to be a disk. And so we've got that the island corresponding to the word I1 up to IK is an ellipse with semi-axes alpha 1 and alpha 2 given by the singular values of the composition of the corresponding linear parts of the transformations. The effect of the AIs is just to shift things about a bit in the picture. And so that means that provided K is large enough so that the diameters of all these islands is less than delta, that means that, well, we've got 2 possibilities. If S lies between 0 and 1, then the delta approximation to the Hausdorff measure is going to be less than or equal to this sum of the larger singular values to the power S, and if S lies between 1 and 2, then this smaller singular value kicks into the power S minus 1, and so adding up over all the safe level ellipses, I get that expression. And so combining these, that just gives me the estimate for the delta approximation to Hausdorff measure to be smaller than those sums. So if we write, I'll use a capital phi SK here for the sums we've got at the bottom there. Certainly we have that the delta approximations to Hausdorff measures is going to be less than or equal to phi, capital Phi SK, at least if K is big enough. However, we now make use of the submultiplicativity, if you'll excuse an 8-syllable word, of these singular value functions, and that transfers to the the fact that these phi sk are submultiplicative. And so we have this inequality, the submultiplicative inequality here, and so from the standard result about subadditive or submultiplicative sequences, this guarantees that this limit exists as k goes to infinity. The kth roots of these sums exist. And I should emphasise that these expressions depend on the linear transformations, and I mentioned in passing an unsolved question is actually whether these expressions are continuous in the linear transformations L1 up to Lm. They're continuous everywhere except on a finite union of well-behaved hypersurfaces, but it would be nice to remove that condition. Anyway, so if this limit here is less than 1, that means that phi sk will be less than 1 if k is big enough, and so that will mean hs delta will be less than 1, and d will go to 0 if delta is small. And so that means that if I find a value of s for which phi s is less than 1, then the s-dimensional Hausdorff measure of the attractor is 0. And so that tells us that the Hausdorff dimension is less than or equal to s, where s is given by solving that. It's easy to see because of the monotonicity of the singular value functions. There's a unique s satisfying that. So that's an upper bound, and one can therefore ask about lower bounds and equality. And so, in fact, one gets a theorem about this. I mean, the example of non-continuity of these dimensions shows that it may be difficult to get a result for all such sets, but at least one can get almost sure results. So we have the following theorem. Let S be the solution of phi S equals 1, where that was as before. Then for all translates, the Hausdorff dimension, don't worry about box counting dimension, is less than or equal to S. And then the other way, provided that the transformations are reasonably contracting, namely that the norms, the induced norms on the linear parts is less than a half for all I, then what you get is equality. Okay, the dimension can't be bigger than 2 if you're working in the plane, but otherwise you get the dimension equal to this value of S. For almost all sets of entiples of translates A1 up to AM, almost all in the sense of, well, in this case it's 2m dimensional, the vague measure, so just putting on the obvious measure on these parameters here. So you don't get equality in every case, but almost every case, provided you've got that condition, and I'll come back to that condition in a moment. You do need that, in fact. There are examples where the norms are equal to a half and the result fails. So let me very briefly indicate the proof of this. We've done it. We've got the first part already. That's what I indicated just now. And so the almost sure lower bound depends on the coding of the points and essentially defining a measure on this. There's a tree given by the finite words composed of the letters 1 up to m, and well, a measure on the sort of limit tree, if you like, and then pulling that measure back onto the sets and showing that things work nicely almost everywhere. So, as before, I'm going to write xai to the point that corresponding to the code I, but remembering that these transformations depend on the parameters ai, and so with the standard notation that if I have two infinite words, I'm going to write I wedge j simply to be the smallest the first integer k where the letters of the word or the numbers of the word differ. So it's the first integer such that I, k and I and jk are different. And so one can, with this notation, you can show that if you integrate over some bounded region of positive Lebesgue measure of these parameters a, the integral of 1 over the distance between xai and xaj to the power s is less than or equal to some constant divided by the singular value function evaluated at the singular value function of the linear transformation Li wedge j, where that simply means the L sub I, I'm writing to the composition of mappings Li1 and Li2 up to Lik. So that tells you where you stop, the wedge tells you where you stop the product. In a sense, what one way of thinking about this is thinking of these A1 up to AM as random parameters, and then you're just really essentially estimating an expectation there. Okay, and then one can use a classical result from geometric measure theory, really an extension of Frossman's theorem, that if phi s is greater than 1, you can put a measure mu on your tree with the property that mu of the cylinder, that's the cylinder corresponding to the finite word I1 up to ik, is less than or equal to some constant times phi s of Li, so less than or equal to the singular value function evaluated at that particular point on the tree. So once one's done that, if s, provided s is less than n, one can look at this integral here, and just by interchanging things and using what I have over there, that means that this is simply the double integral with respect to I, and make the measure on I and measure on j of the reciprocal of the singular value functions, and using this property, this estimate for the measure in there, one can show that if you've got a measure like that, then this double integral will be finite. And so that means if I'm integrating with respect to a, that's finite. That means for almost all a, that integral is finite, and that's an energy integral with kernel 1 over x, distance between x and y to the power s. So by pulling the measure down from the underlying tree to the sets EA, that defines a measure mu A on those sets, and that measure for almost all A has finite energy, and that is a criterion that guarantees that the Hausdorff dimension of EA is less than or equal to S. So that's an indication of the proof in the other direction. Okay, well, let's just look at a couple of pictures. So here's a self-affine set. The fact that they are self-affine sets with the same linear part but with different translative parts. So modulo that the computer only works in pixels, but with probability 1 they should have the same dimension, and you can estimate that at about 1.06 in that case. And then there's another example. I'll put the picture up really because I like the picture. Here's an example where you can show, for various reasons, you can show that at least the box counting dimension actually equals a particular value given by equation, but I rather like that sort of chain-like example that comes from mapping a square just onto either rectangles or parallelograms, keeping one side parallel to the size of the square. Okay, so where do we go from here? Well, we had this nasty condition that for that formula to be valid, we needed the norm of the contractions, or the linear part, to be less than 1. And so let's think about how one might get rid of that. And this is one way of doing this is basically by introducing more randomness. And so this brings us on to the notion of almost self-affine sets, as we now call them. So for a self-affine set, we have these given parameters a1 up to am, just m of them, and that defines an attractor, which I can also write in that way, the union of these image points under, the union of the images of the infinite words under the obvious mappings, where, so xai is again this limit, we've had that before. And now I can expand this expression using the fact that the ti are the linear bit plus the translative bit, and in fact you can express that as a convergent series of points in the plane or wherever. So we can modify this a bit. Instead of just taking m values, a1 up to am, I can change the perturbated bit of this expression at each stage. So let's, instead of looking at our image of the tree defined in that way, let's just modify this formula. So we have now parameters ai1, ai1, ai2, and so on, depending on how far down the iteration you are, and you can expand this in the same way. And so instead of just thinking about these m parameters varying and talking about what you can say at almost all m, we can now let all these things vary in an independent manner, maybe ideal, it doesn't have to be, and then we term the union of these points an almost self-affine set. So the picture here is this construction again, but this time I'm giving myself a little bit of latitude at each stage. So I map my ball onto this ellipse, and I'm allowed to move it around a little bit from side to side, and similarly there. And then at the next stage, I can move this around, but the amount of movement, provided the distributions are IID, the amount of movement will be much smaller at the next level, just the same displacements relative to the parent region, parent ellipse, and I move that one around independently of that one, everything independent, and so on. And we call that an almost self-affine set. And fairly recently, Thomas Jordan, Mark Pollicott, and Carolee Seaman showed, by using a method not too different from the one I indicated, that for almost self-affine sets, then you get the dimension of the attractor with probability 1 satisfies the expression that one hopes. And this time, you don't need this condition of the contractions having to have norm less than 1/2. They only need to be linear contractions of some ratio less than 1. So that resolves to some extent that point, but I'm going to want to come back again to that in a moment. So far I've been talking about self-affine sets, but in fact where they occur in practice and dynamical systems and so on, and you can think really of these things as sort of linearizations of non-conformal dynamical systems, and in fact, there's a whole theory about how you relate the linear approximations to general non-linear dynamical systems. Very often, your attractor occurs with a natural measure sitting on it, and so let's just think about measures on these self-affine sets and so on. So, what one becomes interested here is, well, it's an area known as multifractal analysis. When you've got some perhaps highly irregularly distributed measure across your set, and you want to try and say something about the distribution of the measure. It may be very highly concentrated in some points and very sparse in other points. One wants to quantify this. And one way of doing this is by looking at moments and moment sums. So given some measure sitting on the plane or wherever, I'm going to define the moment sum MRQ to be the sum of the qth powers of the measures in each square of a grid of side R, assuming there's positive, you just sum over squares of positive measure, and I'm going to take Q to be positive to avoid complications here. So we can look at these moment sums, and just as in a sense that dimension tells you about a set when viewed at arbitrarily small scales, we can examine these moments at arbitrarily small scales. And the natural thing to do is to define what are called the generalized Q-dimension or LQ spectrum of a measure, simply giving the exponential behavior as r goes to 0 of the moments, namely the ratio of log mr divided by log r. And it's conventional for q not equal to 1 to divide by q minus 1. This simply makes the numbers you get look more like a dimension lying between 0 and the dimension of the analytic space, but that doesn't have to worry too much. And okay, if the limit doesn't exist, then you have to look at limits and limit suits. And so one can examine these quantities as well. And it's useful to note, in fact, that for Q positive, if instead of taking a sum over small squares of these measures, you can actually replace the sum by an integral. And because if you're integrating with respect to mu, then you have to look at the measure of balls of centre x radius r to the power reduced by 1 for positive q. So that's an alternate, directly equivalent to that. That's easy to show for q bigger than 1. It needs a little bit more work for q between 0 and 1. Okay, so a natural question going on from here then is to look at what one can say about the LQ dimensions of measures on self-affine sets, or self-affine measures if one wants to call them such. So what we have, the same picture, but this time I'm going to define a probability distribution or mass distribution in a fairly natural way on the affine self-affine set. So again, we've got our affine transformations and attractor E, and now I'm going to take a number of, think of them as probabilities. They're all positive and less than 1, and they sum to 1, and we're going to define a Bernoulli type measure on my self-affine set by repeated subdivision. I mean, the picture here is to start with unit mass on the whole ball, split it into 3 parts, so a mass P1 on that big ellipse, that P2 on that big ellipse, P3 on that big ellipse, and then repeated subdivision, so at the next stage you have a mass of Pi, Pj on each of the component ellipses and so on. In fact, an alternative way of defining it is the unique measure that satisfies that invariance condition. It's a sort of Bernoulli measure, and you can see it's going to be supported on the attractor of the corresponding self-affine set. So one can ask what we can say about the generalized dimensions of such a measure, and indeed, obviously one can look at more general measures. You can do exactly the same for Gibbs measures and so on. So it turns out here one has to extend the definition of phi s that I had before to allow for the probabilities to come in, and the natural thing to look at turns out to be, instead of looking at the sum over words of length k of phi s of just phi s, one looks at, you need those terms to the power 1 minus q, so if q is 0 you're just back to where we were before, and then you need the mass on the cylinders corresponding to each ellipse to the power q, and that of course is simply the product of the probabilities pi1 up to pik, which is all to the power q, I suppose. Okay, so those are the numbers one needs to look at, and then once you've got those, we can get some reasonable estimates for the q dimensions. So really this is the analogue of the result we had before. This time we have to use this expression here instead of just capital phi f and equate that to 1 to get a number I'll call sq, and it's again just using the cutting up ellipses approaches and various inequalities, that are standard inequalities to hand. One can show that for all translates the dimension is at most SQ, and certainly no more than n if you're working in n-dimensional space. And then just as before for the lower bound, at least if q lies between 1 and 2, we've got this restriction on the norms of the transformations, then again for almost all entiples of translates one gets equality there. And the proof is not too far of an extension of the version for sets, cutting up ellipses in one case, and then to the other estimates one simply has to look at the integral over all a, or the expectation of these moment integrals that come in there. Okay, but it turned out that the case of q bigger than 2, the q dimensions turned out to be rather more awkward, and let me just indicate briefly what one can do here. So the basic problem is that you're not going to get these results at higher moments unless there's more interaction between different points in the attractor, different points carrying measured in the attractor. And so in other words, one needs more randomness. And it turned out that the almost self-affine structure was precisely what one needs to extend these results to larger q. So now I've got a Bernoulli measure again, repeatedly dividing your mass in ratios P1, P2 and so on an almost self-affine set, but now I'm at liberty to move around these individual islands slightly in the way I did before. This island there can be expressed in terms of the two linear parts and then the two translates where they are now independent. And the conclusion one gets here that in this situation Provided you're working on an almost self-affine construction, then for almost all A in the you're now working in this probability space with infinitely many I1, I2 corresponding to the shifts, the translated bits at every level. For almost all A, then the Q dimensions are indeed what they ought to be. Well, I've already mentioned that the upper bound, as usual, does not present any problem. The lower bound actually was rather more interesting. And again, one tries to estimate the expectation of that moment integral. And firstly, one can show that this expectation can be bounded by a power of r. And then I'm simply going to take q to be an integer n. So n and q in this case is the same integer, and for q non-integral it's a little bit more complicated. We can show that the expectation there is bounded by an expression I'll call phi s I1 up to in, and integrated over all points on the boundary of the tree, all infinite words I1 up to in the case where n equals q. And then this expression here, this phi s, is simply the product of the singular value functions at certain points on the tree, which I call join points. So you've got in this picture I1 up to I6 at the bottom, and there are always 5 points somewhere in the tree where if you take any pair of these points at the bottom, let's take that one and that one, say, then they meet at one of those 5 points on the tree. If you have n points at the bottom, then you've got n minus 1 joint points. And so one gets this expectation bounded for there by that expression, and one has to do quite a lot of work to estimate. Once one's got this integral there, which involves these singular value functions, one has to do quite a lot of work to estimate that and show that we get what we want, namely that this result here holds. So that's really what I want to say, starting with the notion of self-affine sets. We've gone through almost self-affine sets, and then self-affine sets, almost self-affine measures. There are still plenty of questions that are unanswered in relation to this, but at least I hope it gives you an indication of the sort of thing that I work on. Thank you.
Thank you for a very clear talk. Are there any questions? No? Well, if not, let's thank the speaker again.